Parker, tell us what MS is. Mr. White, David White, sorry, there's two Whites right here. David White, you're up next. And Randall, you're up for the last one there.
That's North Carolina. I take it this is quiz review.
A wise man. What does the Bible say about a wise man? Oh, a word to the wise is sufficient.
Yes. Rick and forfeits.
A word to the wise is sufficient.
Amen.
Ooh, I don't know the address.
I don't know.
Give me a sec. I can see it. All right. Thank you, sir. And is referencing what type of hardware?
Fitting.
Fitting and bolt. Good. MS is referring to what?
Special fittings.
Yeah, special fittings, special fasteners. Okay. You could get bolts. You could get nuts. You could get a wider range there. NC. What is that all about?
Coarseness.
What's coarse?
Thick or wide.
Yeah, a little thicker threads, wider, typically a little wider teeth going into it. Yep. National fine threads, a little bit finer, more threads per inch. Okay. Let's ask geese. Okay. What is the shank?
More specific.
What is the shank? What is referred to when we say the shank?
The grip and the thread.
The grip and the thread. What portion holds between two pieces of metal? What is that portion referred to? Portion between the two pieces of metal.
Grip.
The grip. And when we're measuring a bolt, we measure it based on what?
Grip and thread.
The shank diameter. Diameter of the shank.
Specific. Appreciate it.
All right, you're welcome. And that's in what unit of measurement, Cheddar? Good. And the length, Grant, is in what unit?
8.
All right, good deal. Ooh, had me nervous there for a second. All right, what item or fastener is used to secure a castellated nut properly?
Out of it.
Out of that. If you're reading Christian Reif Smith, if you're writing an abbreviation for a bolt with a hole through the head on the propeller, what is that letter of abbreviation?
H.
H is correct.
That's a hole in the head of the bolt.
Nailed it.
Yes, ma'am. I have a note in here pertaining to the 4 types of aircraft bolt categories, and I have it written down, AN, MS, NAS, NS. Is that a separate, what's the relationship between those categories and these?
So AN is typically what you're going to use, okay? MS, you can get it as a converted bolt. Sometimes MS will be used. I can think of dozens of times where MS is used. But MS covers a pretty wide category of like nuts and bolts versus AN specifically covers mostly bolts or like fluid fittings. Okay, then when you get to NAS, NAS is going to be a specialty bolt. For example, if I'm ordering bolts for a light-holding engine, 90% of those bolts are going to be AN bolts. The other 10% are going to be a specialty bolt. They're going to be usually an
four bolt categories, why are we not including NAS up there and S up there, or is it like a separate distinction? Like this, you're saying this pertains to the threads, so do these four categories pertain to?
No, those are also categories. I'm just trying to review the quiz.
Okay, so really there's six categories. MS, MS,
Yeah.
MS, AN, NC, NF.
No,
S and NAS.
stop. NC and F will cover, these are not just categories, these are reference to what?
Reference to what?
Yeah. What are they reference to? What are these references to? This is not a category of bolt as much as what?
The thread.
Thread. And that will cover, when you're looking at a bolt, it's either fine thread or coarse thread.
Okay, so the four I listed are specific aircraft bolt categories.
Yep.
And these four are specific to aircraft bolt thread.
You're gonna help me out with it, thank you. All right. Ms. Dennison, what's the maximum height of washers when you're torquing a bolt allowed, according to 8.13? 1/8. All right, that's it. Probably one of the shortest quizzes I get. All right.
Is that it?
Those categories, the last one we have. No, what's special?
NAS?
Well, NS, but then there was S. Special.
That's right, yep. I'm trying to remember where it is on the book here. Yeah, so page 7-10, if you wanna look it up. You get to NAS, you get to close tolerance, NASs. Right. Let me pick someone else here. Oh man, they're all mixed up. All right, Jordan, come on down, buddy. Oh, by the way, you will be given bolts on the test to be able to have to measure, okay, or on the quiz, rather. All right, so we're gonna check to see how close Jordan's torque is here. So we want Jordan to torque this bolt right here to 120 inch-pounds. 120 inch-pounds, okay? So give it a shot. Let's see how close you get. Okay? Then I'm gonna do it the other one. We'll get another candidate to come check us. 120 inch-pounds. Israel, come on, buddy. You're gonna check us. All right.
I don't know which one else to do.
All right. Is that it? You good?
Yeah.
All right. Good deal. All right, let me do mine. We'll see who gets closer now. Is that yours?
Yeah, that was
Okay. Oh, there.
I think.
Oh, did you?
Yeah.
Okay.
1.1.
All right. I gotta loosen mine up.
Oh, he's confident up, dude.
No, the goal is to get within 5 if you can.
I
Alright,
think
grab
that
something.
is. I knew 21.
Okay, so this one and this one. I got the hole in the head. Oh, you need to. Alright, you get the prop. Let's see what you're doing. Prop. Alright, you're on? Yep. We'll check our torques. Oh, 108 on the first one off, right?
Whoa.
Good deal.
Whoa.
Alright.
Is that calibrated?
Oh, 101. I was lower. try to do it by hand, you'll typically under torque it. And I think even the book states that very clearly. Thank you, Israel. Is that when you try to do it by feel, typically you're going to err on the lower side. Interesting. So, even though you get a feel for it, you don't always get it right. Okay. All right. Any questions about torquing? No, torquing is not going to be part of your quiz. Any questions at all? All right. We're going to move on to bigger and better things. I will warn you, I will not get through this lecture today. I have 94 slides. Usually about 3 hours is 40 slides. So again, to give you an idea of how much we have. So in order to keep you engaged, we're going to do two things. First of all, I am going to go over this in-class handout. If you'll open Moodle, Lab 144-5. Looks like this. It says you better listen. All right. So we want you listening here, and you have 4 whopping questions. Okay. It does count as your grade for submission. This one is expected to be done when I'm done lecturing today. Okay. All right. So before we get started, I'm going to give you about a 10-minute break. A little over 10 minutes here. But the goal is while we're going through this information, it is important, but the only way I typically keep students engaged is to keep you filling out information, especially when we're talking about heat treatments. Because let's be excited. You know, being real is it's really difficult to keep it exciting as far as materials and heat treatments. But it's super important. For example, on the full 14, if you walk up to the tip tank, there is aluminum brackets that hold that tip tank on. 3 bolts hold the tip tank on out there. You can actually torch the aluminum to be able to bend it without it cracking. What temperature can I put it to? Well, that depends on what material is cladded or alloyed with the aluminum. If it has copper in it, it will bend and will hold. If it's pure aluminum and you put a torch to it, it's going to melt right down. Okay? It's going to break down. But they all look silver, they all look shiny, they all look, pretty. And so, kind of what we'll hit today. Take about a 10-minute break, grab a cup of coffee, or 2 cups of coffee, whatever. Joe, grab your gallon of milk. You gotta do it. You gotta do it.
You're right. Pure aluminum, does it burn or just melt? I mean, like if you like aluminum foil, you clump it up, you throw it on the fire. Eventually, it kind of flakes away.
But aluminum foil is not pure aluminum.
What would that be? Would that just be low grade?
Yeah, low graded
Tinned aluminum or
sheeting,
something?
tinned aluminum sheeting.
So pure aluminum,
Is super soft.
super soft.
Oh my gracious, soft.
Doesn't stand a chance of getting any heat.
No.
No.
I got it.
Ooh, 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 ooh.
I've had private retreat and any book. I don't know how that's possible, but
They just get COVID on one. Oh, I know this. Oh my. my window's up now?
I hope not.
Doing pretty good. I drove my old truck, half the time I had the windows down, so I was like, oh. Of course, there wasn't any electronics and folders. Right? Couldn't hurt anything. That one? No, I just started that. No, it's fine. Yeah. I had to ask him too. Yeah, yeah, there's other manuals that say the same thing. Those are the ones we're looking at.
Oh, he's walking the back.
I pulled up the trap manual. I was trying to figure out, it's like trying to figure out the right page. It's like page one, is that, and there's a page beside it.
All right.
Is that what you are? You should know I'm from Georgia.
Yeah.
Dude, you see how hard it is? Ryan's from Georgia. You see how hard it is?
Then I realized.
You guessed A&3 was All righty. Let's get on the road. On the road again. All right. Aircraft metals, specifically aircraft metals that we're using it to be able to assemble an aircraft, or how the aircraft materials are assembled together. Okay. Types of metals, properties of metals, and purpose use of types of metals. Okay. So every time you come in for a landing and you pound that aircraft into the ground, thinking, oh, what material just got bent, right? You ever thought about that? Or you thought, oh man, poor mechanic's gonna have to figure it out. No, you say, oh, job security, right? What material is getting bent? Students need to understand the different types of metals used in aviation. Students understand the importance of the metal types, composition, and learn the major terminology as it relates to metal and treatments. You have to know all the treatment types. You won't. Okay, maybe one or two of you will, but it's not required, okay? All right, so references, we're in chapter 7 of your general book. If you want to follow along there, you're going to spend lots of time in there for the lab anyway. 7172 through like 722. Properties of metal, hardness. Give me a type of metal material that's used in aviation. Aluminum, good. Aluminum. Stainless steel. Where is stainless steel often used?
Hot areas around the engines also. Or exhaust.
Exhaust. Sure. Okay. Firewalls. What other material? Titanium. Where's titanium used?
Non-oxygen.
Non-oxygen. Where's titanium used? Negative. Where's titanium used? Anyone know? Oh, come on, Lou.
On the big aircraft, we use as part of the struts.
Okay, smaller aircraft now, all 172s are going to landing gear, titanium, and as well as Boeing 787 is going to titanium landing gear structure. Yep, what else? also, yes, okay, contactors on some of the aircraft are using gold for the contactors. Don't go melt a bunch of plastic down and figure out where the gold is. Copper, where's copper used? Okay, good. All right. Yep.
In our
Wires as well. Yep.
as well. In our aluminum.
Yes. Aluminum.
Magnesium.
That's something.
Where's magnesium used? Rudder pedals. Where else is magnesium used? Oh. Yes, they were used on control surfaces. Unfortunately, they're still there in circulation on control surfaces. Any others? Any other material used?
Carbon steel.
Carbon steel. Okay, where's carbon steel? Good, carbon steel cables.
Pretty sure silver is used in some maybe others. There's some wiring.
Yeah, some of the wiring, silver solder or silver based. Yep. What about chromoly-bendium? Chromoly-bendium steel is used on all landing gear on the smaller aviation. Okay. Every time you're doing that bouncing landing, you're just super glad that GM and Ford did not make that landing gear. They were not made to bounce. Isn't that right, Jonathan? Okay, yeah. All right. So strength, something may be super hard, and oftentimes you'll say, "Oh man, that's super strong, very strong." Just because something is super hard doesn't mean it's super strong. This is magnesium. It's light and it's hard. Very, very light. Very light. But it's super brittle. You would drop it right here. Wait a second. I thought you said it was strong. It is. But it's also very, very brittle. Why would you use that on a sump? On an engine that's always doing this. It was used in the 40s only for a few years. Yeah.
You say strong, you say like up to a certain force, it won't then get any dents to pass the force.
Good. All right. So the reason why we're being vague is because oftentimes we use terminology in our English language just like, "Oh, it's super strong." Well, yeah, it's strong. But what do we mean? Strong, brittle. You know? And so that's kind of what we're shooting at today is kind of understanding how each one relates to each other. Okay? Why do we use steel or why do we use aluminum casing now instead of a magnesium? Well, magnesium was super nice because it was super light. I mean, super light. Okay? But as you can tell on the bottom there, it's had to be patched up. Okay? This would be off an 0300 C145, so this would probably be off what Clayton's dad's engine, or same sump on it. Yep. Density, malleability, ductility, elasticity, toughness, brittleness, fusibility, conductivity, and thermal expansion. You thought you only got that in basic electricity. No, we're going to get some here now. Okay? So, first terminology just for kicks and giggles. Yes.
Do we need to commit this to memory?
Bam. There you go. No, we're just defining terms. Hardness. So what is hardness? Resist abrasion. Cutting. Penetration. Permanent distortion. Something's very hard. Okay? Something, if you're banging on something really, really hard, talk about something that's been carburized. What is something that's been carburized? What is that referring to?
They dump fuel injection
No?
with carbon added through the alloy.
Yes, carbon added to the exterior of a material. Okay? The material is already done, but on the outside of it, they'll heat it so that it will be carbon, or exposed to carbon on the outside. And what happens is it creates an outside exterior protective barrier. So the internal composition of the material could be soft. Okay? Parts are often soft and then hardened using typically a carbon style.
Cold working increases hardness of material. Okay? So, you take a piece of metal, all right? It's been exposed for years, and you start doing this back and forth and start bending it. What happens to the material? Well, first, before it snaps, you always go to the extreme. Well, before it snaps, what's happening right there at the little bending point? It's getting hot. Especially if you're doing it real fast. You know, it's like back and forth. And it's getting really, really hot right there at that joint. And then, as it's getting hot, what's happening? It's hardening, getting, and then all of a sudden, snap! Because you've worked through that material, and we've gotten to a point where, okay, that material that we're bending on and cranking on is meant to hold straight. And it's been hardened on the outside, but what are we actually bending against? Is the internal composition now. We're trying to break the external, holding the cold form inside, or cold material inside. Outside's been carburized or hardened, and you're trying to break down that composition. That's why when it gets hot, and all of a sudden, snap, because you basically broke down the internal structure right there at that bending point. Okay? And so, cold working increases the hardness, rolling, hammering repeatedly. But if you do it too much, end result is it can become brittle. Bam! Breaking. Strength. Strength is the ability to resist deforming or deformation and stress without breaking. Strength of material. Okay? For example, that sump. If you take a hammer to the sump, if I take a hammer to that oil sump right now, it's going to give in. Okay? All right? Its strength, it's very, very strong on the surface, but man, does not resist deformation as a whole. Okay? Density, weight of a unit, volume of material. It's very light. Okay, that material over there, magnesium, is very light. Density is important in our aircraft material. Why don't we build steel aircraft? They don't come off the ground. Okay? It's not impressive to say we have a 10,000-foot roll in a Cherokee 140. It's not impressive at all. It's impressive to say, hey, we have a 1,000-foot roll in a Cherokee 140. Okay? Important in aircraft because lighter weights are desired. Malleability. Malleability is the ability to be shaped without cracking or breaking. Play-Doh is malleable. Some of our mines are malleable. Copper is malleable. It's important for sheet metal that is formed into curved shapes. Here's a piece of aluminum that has been formed. Okay? This is, and it was heated to a certain degree point. Not enough to break through the protective coating, but then it was formed. The gusset. I don't know what it's for. I can't remember what the gusset is for. But super light and super strong. Okay, malleability. Ductility. Ductility is the ability of metal to be bent, drawn, twisted without breaking. It's similar to malleability, but it will withstand shock loads very well. Okay? That's ductility. Important for formed or drawn parts. Elasticity. Elasticity. Ability of metal to return to its original shape and size after bouncing down the runway. Okay? So, come in for landing, and we botch the landing. Bam! 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 You know, 4 touch and goes during one landing, right? Okay? How does that landing gear always hold up? Well, thankfully, they are spring steel, hardened spring steel like this. And then on the outside of it, they are formed with shot peening. So they put even a harder coating on the outside of that material. Now they're going to titanium because they've realized that pilots will still break landing gear. So they're going to titanium to make it lighter and also stronger as well. Okay. Ability to return to its original shape and size without breaking, but of course there's an elastic limit. Toughness, ability to withstand bending, stretching, deforming, or deformation without breaking. Toughness. What is that definition close to? Strength. Very close to strength. Okay? They're very closely related. Brittleness allows little bending or deformation without breaking. Not desirable. Ice. Ice is brittle. Magnesium is very brittle. Fusibility, ability to become liquid with application of heat. So steel becomes liquid. What's the famous saying by welders, right? Can't be tight if it's liquid. Isn't that the famous, like, that's what they say, right? It's not, yeah, it can't be stuck if it's liquid. Can't be tight if it's liquid. All right. So steel becomes liquid at 2,600 degrees. If you add the same heat to aluminum, it will turn to water. No, aluminum becomes liquid application at 1,100 degrees. So very, very different.
Do you have a low temperature? What is that?
Yes, I know what you mean. Yes. There's other thoughts, but yes. Conductivity. Ooh, a good conductor does what? Carries heat or electricity well. So important for welding. Conductivity. How does a welder, give me the elementary first grade version of how a welder works. Two pieces of metal put together. Okay, great. But we need something to put them together. Yes. David, White?
He like melts metal that binds the two pieces.
Good. So, yes.
Yeah, it uses arc.
Uses an arc, an electrical flow to put two pieces of metal together. Okay, those of you who are missionaries, you can actually weld with a battery. Okay, super common to be able to do it. I've done two batteries back to back to be able to weld a trailer back together. So put positive, negative on the battery. Put your ground from the one battery, so you get 24 volts. Put positive and negative together on the battery, you get 24 volts. Then you run your negative to the material you're getting ready to weld. And then you take your other jumper cable, put your welding rod in it, and watch your eyes. And you'll be able to weld. And what are you doing? You're literally creating what he said, an arc. Okay? It's an electrical flow. Now, if I do that to wood, what's going to happen? No. Nothing. Whose electrical class are you in? Wood does not carry current. Wood does not carry current, right? If you put the negative to the wood and you put the positive over here, nothing's going to happen. Yes?
What if it's wet?
Okay, if it's soaked in water, what becomes the conductor then, sir?
Water.
The water's the conductor, okay? All right. But wood itself, nothing's going to happen, right? Because you're connecting it two different places. Okay, it's not a conductor. But if you do that to steel, it will be a conductor. Aluminum, a very good conductor. It will only be aluminum for just a second, okay? Then it becomes liquid again. All right. Anyway, just food for thought there. It's not, that was free. All right. Thermal expansion refers to the size of material growing and shrinking because of temperature changes. Okay? Something in Texas is going to expand and shrink, actually expand a lot more because of heat than it will in this frigid state. Okay? Different metals have different degrees of shrinking and expanding. But then, as you can tell from our 414, too much time in Texas will remove all of the paint. Okay? Metallic composition. How is metal formed and bonded together? How is it formed and bonded together? How does that work? Let's talk about that. All right? Metallic composition. How is this material bonded together? Okay, we'll look through various stages of it. Not real, like, not intricately to the point where you're in a shop and you're making metal itself or bonding metal together. But in your book, I want to say, yeah, 7-4 is a huge chart of metal compositions, okay? And you'll get a 4-digit number, which we'll get through today too. For iron-based metals, refers ferrous metals. Ferrous, what is ferrous?
Has iron as a base metal.
Has iron as a base metal. Put it in first grade language for me. Magnetic, ooh, yeah. All right, and what else? When it's exposed to water, what happens to a ferrous material? It oxidizes. All right, first grade, remember, we're talking first grade here. Rust. It will rust, okay? It's rusty. Good. Or it's Michigan, right? All of our vehicles, right? Okay. All right. It's a ferrous material. Okay, sorry, not the Ford. Thank you. I realize. All right. The Ford wants to go to the aluminum minus the frames, whatever. All right.
I'm still working still.
All right. Anyway, refers to iron-based material. Iron is primarily ingredient. Carbon and other materials can be added approximately only 1%. Because is carbon actually hard? No. But when it gets heated and added or exposed, you get a carbon dioxide gas around the metal material, and then it reacts. The metal material then sucks in that carbon dioxide to create a hard coating. Do you need to know that? No, you don't need to know that for this moment. Mixture of materials is called an alloy. If you say you have a metal alloy, that just means it's a mixture of metal materials. A mixture of metal materials. Changes chemical or physical properties. That's why when you turn a torch on and it becomes liquid, why does it become a liquid? Why does it become a liquid? I get a bolt and it's stuck in a hole. Okay? You get a bolt and it's stuck in maybe an engine case or in let's pick on Michigan, a brake caliper. Okay? So you light the torch and you all the way through it. What's the point of doing that besides having fun? When I turn it all on full blast, I don't want it expanded no more. What do I want? I want to break down the molecular composition in there until it basically gives up the ghost and says, it's beyond heat. And the head falls off, all the guts fall out, and then the part comes off the vehicle. Okay? So I'm going to change it so that there is a critical temperature. We're going to get into this fine line maybe today, where there's a fine line in a specific material. Okay? Put a fine line. For example, landing gear. Let's pick on Kurt. Kurt just finished his commercial. Okay? He comes in for his landing and botches that landing. Okay? Bam! All right? Does a botched landing. So then when we go out there, we say, you know what? We're going to straighten that landing gear for him. So we get out our torch and we start heating it. And we're going to do, the redneck way of straightening it. So we'll look at it and, use a calibrated eyeball and get it good and straight. So we get it good and straight. He goes out, and the next time he does a landing, it falls off. Okay? That's not a good scenario. Why did it fall off? It's actually not his fault. It's because on the outside of a landing gear, it is shot peened to protect it from from external, like rust, corrosion, water damage. And when I decided to, turn it almost liquid to get it straightened back out, I broke down that protective outside coating. Okay? And then I started melding that outside coating into the internal structure, which then broke down the internal structure to say, oh man, we're exposed to a heat where we cannot basically spring anymore because we're breaking down in that one little portion. And typically it's going to break right there or break really close to where you broke down that molecular structure. Okay?
I like pressure and stretching of the material, like because of the difference in.
Correct. Certain alloys have stretching, yes, correct. But the moment that you add an external, so it's treated to a certain temperature. It's supposed to act like this all the time. And then all of a sudden you bring it back up to its critical temperature. Maybe it's 2400 degrees. Not quite liquid, but 2400 to get it to bend. Now I'm breaking down that protective coating. Okay? So which means it's melding, it's changing the properties right there. Even though, man, I can paint it and make it look beautiful. Cover up all my sins until he comes back to land, and then all of a sudden, bam! Why did it break right there? Well, it wasn't his landing that time. Right? So that's fair. But the point is it really comes back on us as mechanics if you're breaking down a molecular structure. Still, identification, 4 and 5 digit identification numbers. That is on the page 7-4, what I just referred to. Yes, sir.
You're saying shot peening?
Shot peening, yep. Shot peening, yes, but it'll be down the road,
That was great.
long down the road, like 2 months. So, go ahead. Is the alloy. Yep, steel alloy. Okay, 7-3 gives you 4130 or 4000 series chromolybendium. Is that what it is? Chromolybendium. You get 5,000. 5,000 comes back out. 5,000 becomes what? Magnesium based.
I'm not sure.
Let's look at your table.
Yeah, Molly, 3.25, 0.4.
You get to 5,000 carbon chromoly here. 3,000 is nickel based. Ooh, nickel. Do you know stainless steel is a nickel based? That's what makes it so shiny. Those little nickels in your pocket, okay? It's nickel based, okay? Does it have steel in it? Does stainless steel have steel in it? Yeah. Yeah. And depending on how much steel is in it, is how magnetic it is. So if it has a lot of nickel in there, it will have a very strong outside coating and it will not be reactive with a magnet, okay, because of the iron content. Okay. What do these numbers mean? Well, simplified, the numbers mean they identify first, number 1 indicates the carbon steel. Carbon steel, number 2 indicates nickel steel, number 3 indicates nickel chromium steel, or, I already put it, chart 7-3, or is it chart 7-3? The chart's labeled 7-1, yeah, okay. 2340 would be a nickel steel, 2000 series, nickel steel. Second number indicates a percentage of a primary alloying agent. So, 2000 being a nickel steel, 2000 here, the first digit, that's the thousands digit, okay? Then we go to the hundreds. The second digit, then what percentage? Well, it's 3% nickel. 3% nickel. Okay? And then the last numbers is where it gets slightly confusing. Indicate the carbon content in 1/100th of a percent. Heads up, this this is only for the ferrous materials. We go to a different set of rules for non-ferrous materials. What's ferrous versus non-ferrous?
Someone else said about iron.
Iron content. So is aluminum a ferrous material? Non-ferrous, good. All right. So the last two digits indicate carbon content in 1/100%. That's insane. Okay? So if it's 40, then it's 0.4. If it's 2303, then it's 0.03%. I know, it's Tuesday morning. All right. Remember, total carbon content is usually less than 1%. So this is the case, 40% of 1% or 0.4. All right, as I already referred to it, other materials that can be added: copper, nickel, chromium, molybdenum. Now, what is copper? What would you add copper to a metal material for?
Give it, flexibility,
Flexibility,
heat resistance,
heat resistance,
Maybe conductive.
conductivity. Little carry current or amps. Amps. Okay, a little easier.
Hold its shape once we bend it.
Sure, if you need to bend it, you would put a copper in it, yeah. Metal material itself would be, yeah. Yeah. Copper so it can bend.
Right.
And then the metal will hold it there, yeah. All right, nickel, what is nickel? What would be the point of nickel? Jedediah is over here firing them off today. Go ahead.
nickel gives it, strength, rigidity.
Where at? Specifically.
Like on the aircraft?
No. Like, when you're doing a material with nickel, what would be the point of that? Is it as hard as carbon steel? Why would you use a nickel instead of like a carbon, or cobalt?
It has less of it's less brittle.
It's less brittle.
Carbide.
It is, unless it's exposed to heat, but yes. It's less corrosive. Nickel's very resistant. When's the last time you saw a nickel that was like platted in rust? That's pretty amazing, isn't it? I mean, dig them out of the dirt, and it's like clean them off in a little vinegar, bam, there it is, pretty again. Okay? Chromium. Anybody ever heard of chrome? We don't put chrome on cars like they used to when they really had masterpieces, huh? All right, a little salty there. So, it's almost a lost art. What's the purpose of chrome? Heat resistance. Okay, yeah. What else? It is shiny, but okay, thank you for the looks there, but what else is it? What? Strength. Is it resistant to like water, and it's resistant to, it's got this outside coating on it oftentimes. Yeah.
It's not being dumb, I guess, but since it's like super reflective, maybe like with sunlight, maybe like.
I wouldn't say that's stupid, no, but because of the coating, it's resistant to, outside elements.
Gotcha.
Water, sun, yeah. All right, and then molybdenum, we'll get into that one. That gives it a very strong internal structure there. Okay? Exceptions abound. Just like screws and bolts and nuts, exceptions abound with materials as well. Sometimes the first set of numbers doesn't follow the pattern. So that's why we come up with 8,000 and 9,000 series. It just means it's a rule breaker. Rule breaker. Okay? I've taken this one out of the curriculum, but I will share it with you on the next slide here. All right. Testing different alloys. to go to the aircraft and say, you know, I'm not real sure what material this is, so I'm gonna grind it. So we've taken that out because it's not a real life scenario where you go out to an aircraft and you say, man, I'm not really sure what that engine mount is made from, let me grind it down. Okay, highly unairworthy when you do that. So still can be spark tested on a grinding stone. It takes experience. If you go out and grind it, you'd say, man, did that spark a little or did that spark a lot? I don't know. Okay, yeah, yes, sir.
Pertaining to the second number, it says that, yeah, so is that always a one digit? So is it equivalently, is it always less than 10%? This in this example, it's
No,
3.
sir.
Okay.
All right, good, answer, all right. All right, so this is the one, is this still in your book? Is this picture still in your book? This picture was in your book for many a moves. That talked about spark tests. So, high manganese steel will have beautiful ray of sparks. Okay? Cast iron doesn't have a whole lot of sparkage. Okay? Cast iron. Tell me qualities of cast iron. Give me what's the qualities, James?
Brittle.
Very brittle, but heavy almost as lead, isn't it? Yes.
It's use it for cooking because it retains heat.
Retains heat. Very well. Good. So a medium carbon steel, you get a mild stroke of sparks. Okay? And then you get to a mild steel itself and you get less. So more manganese, more bright colors. As I said, we're not doing a grinding test because you're not going to look at that and say, you know what, I can't tell if that was 3% or 4% manganese. There's no way you're going to know that. Okay. All right. So when you guys were cutting off your flexible hoses, did you think about how much metal material was causing sparks in there? No. All right. So it's really difficult. Testing different alloys, steel-based alloys, stick to a magnet. There you go. Stainless steel is an exception. Is it always an exception? Can I have your magnet? Did you bring your magnet with you today? Up. Can I borrow this, please? Sure. So, have you noticed that these cute little things say stainless steel on them? Have you noticed that? But bunch of liars, right? Is what you're saying, bunch of liars. And it holds really well. Is it really stainless steel? Oh, well, it's stainless steel coated. So inside becomes that material itself is actually an iron base. Mostly iron base with a pretty outside nickel base. Okay?
Right.
Yes, sir, Thomas.
Like if you're looking for a true stainless bolt, not just plated,
Sure.
what kind of
Magnet. Por favor. Okay. But I'll lose it and then I'll feel bad.
would it have like a number or something?
This is almost solid. Somebody else has it now. It's not. We have video though, if you
Very
can't
little.
figure it. Very, very little. Enough to make it strong, but it is coated. Okay. Pretty impressive, isn't it?
Yeah.
Oh, it's trying to come off. Look at that. All right. Can you pass it around? Let everybody play for a minute. It'll keep everybody involved. It's good. All right.
Very nice.
All right. Types, characteristics, and uses for steel. Low carbon steel. Low carbon steel is a 1000 series. Safety wire, which we don't really do safety wire as low carbon steel anymore. But the point of that one is we want safety wire to be strong. Most of the time, safety wire is all stainless steel. Not all. Ooh. not all, I just have to rephrase that.
Isn't there nickel?
There is nickel, but there's brass. Brass. Every time you have an emergency handle, and the reason why is because it was a dad with kids that had to put brass safety wire to keep their kids from opening the emergency hatches mid-flight. So we use brass safety wire so that an adult has to come along and break the safety wire. Same thing with the emergency brakes, they're all brass safety wired because of kids pulling the safety handles, okay? Or students. Medium carbon steel goes to 0.3 or 0.5 carbon, and it's 1000 or 1035. Good for machining or forging. What is forging? Yes. Caleb?
Swords and knives and stuff.
Oh yeah. Okay. Yeah. Making swords and knives. Okay. Creating something, banging something into a shape or form.
So it's a hard landing, a form, and forging.
It has to be.
It would be considered decimation. All right. All right. High carbon steel, 0.5 to 1%. Okay. That's when we're really not wanting anything to penetrate the outside of the steel. Okay. Very hard when heat treated. Good wear characteristics, but and it will withstand a shear load, but it's limited use in aircraft. Used for flat or coil springs, landing gear. Okay, flat spring, coil spring, flat spring or coil springs. We want them very hard and withstand a shear load, but inside of it, sometimes it can be soft. Nickel steel. So nickel steel increases the hardness, the tensile strength, the elastic limit by having nickel in it, and heat treating is more effective. And it's used in so many aircraft hardware. So, because the aircraft hardware looks pretty, doesn't mean that it's necessarily what? Stainless. Actually, they're not. They're just nickel coated to prevent the outside of it from being subjected to corrosion. Okay? So it's pretty. Oh, so pretty. That's why it's corrosion resistant, is because of the nickel within it. Those little things that you had to look up for the lab, they actually mean something. It means it's supposed to withstand corrosive material. Okay? Chromium steel, hard and strong, corrosion resistant, and is used for bearings. Okay, it's out of a radial engine here. So when you look at a bearing, especially like a prop bearing, or you look at bearings in like wheel bearings, you'll see how shiny they are. And that's because the outside of them is supposed to be corrosion resistant. You want them to be able to carry a load and not wear. So it's very hard. It's also very corrosion resistant. Okay, this one's a little bit seedy. Yeah, it needs some grease. Okay, but these are already starting to break down those bearings. So chromium steel, often used for bearings because it's very hard and corrosion resistant. Okay, able to transfer that load. Chrome nickel or chromium nickel, stainless steel, 18-8 corrosion resistant steel. That's where we're getting into some pretty cool mixtures now, where we get to stainless steel. We're getting into what's the new exhaust that they're doing? It's not stainless steel anymore. They weld them in Grand Rapids for the Ferraris. they're doing stainless steel and not Cermachrome. It's, but I have the chart in a second. But they're actually using a chromium and nickel, or they'll use a stainless steel together to be able to make an exhaust system. It's pretty cool. And actually they're changing exhaust right now on one of your 172s for the flight. And it's about $1,800 or so for exhaust muffler. And it's stainless steel, highly corrosion resistant. But the problem with it is if they do a hot start and they add fuel to it, and that's what happened here, if they did too much fuel with a hot start, boom, blows it out because it's not forgiving, okay? It's corrosion resistant, it's very hard outside coating, and it gets exposed to extremely high temperatures, then it will deform, okay? Strength is increased by cold working, so hot starts usually destroy the mufflers. Okay, magnets do not stick to pure stainless steel. Pure. All right, you ever seen this? Stainless steel chart here. Okay, so there's quite a few derivatives of what they can add to stainless steel. Chromium vanadium, steel. Okay, so we have 18%, we have 1% chromium, 6,000 series. When heat treated, is strong, tough, resistant to wear and fatigue. Used for springs and roller. There's roller bearings passed around, or ball bearings. Okay. All right, this one's also an oral question. Chromoly steel, strong, tough, wear resistant. What's the most common steel used in a landing gear? You'd say 4130 or 4000 series. 4000 series. Chromoly bendium steel. Chromoly steel. Easily welding. Very easy to weld. Tubular structure. Tubular structure of a fuselage is typically 4130. Very, very thin wall, but extremely strong. The downside of it is it's extremely susceptible to rust or corrosion to the outside. That's why it has to be painted, treated and painted pretty quickly. It's good for high temp service engine mounts, but it's got to be painted and protected, okay? Inconel, that was it. Stainless steel and Inconel. Inconel is what they're using for the, like the Ferrari exhaust and some of the new stuff. Yeah.
You said chromoly steel, is that what you said was used for oleo struts as well?
Correct.
How come it's shiny and it's not painted?
Chromoly. Bendium. Chromoly. They put an extra chrome on the outside. That's why we go to chromoly bendium. So on the outside, they go ahead and plate the outside for chromoly. 45606, so it won't corrode the actual, like a fuselage will get corroded. So they're putting a chromoly even on the outside of that. And chrome sticks to that very well. If you pull off, like, you know, my family has a 1965 Ford Mustang. If you pull off those bumpers, those chrome bumpers inside of it, you're not going to see any chrome. What are you going to see? Rust. Right? Why is that? Because they plate the outside where it's exposed to most of the elements. Inside, it's not. So kind of the same thing that they did with the oleo struts. They wanted to coat the outside so that it would be resistant on the outside. Yep.
Doesn't the chrome hide cracks because the metal will crack but the chrome will not?
Yep.
So isn't that not a good thing? I know for spinners it's really not supposed to be chrome.
That's right.
So why wouldn't it be like that?
Now, why wouldn't they want it chromed on the spinner?
Because if that cracks, you've got big problems.
No, that's not it. Vibration. Constant vibration on the propeller versus landing gear. What do you have? The only vibration is the pilot, jamming it on the runway, and that's only optional. No, landing is mandatory. I know, but very a temporary thing versus your prop spinner's always, hopefully always turning. Hopefully always turning. So that's another reason why we're using 4130. It takes the initial drive here. You don't have necessarily a vibration. It's just a simple up and down. Yep.
Would you mind going back to that chrome vanadium steel slide?
You betcha.
The vanadium steel, the chrome vanadium? Thank you.
Yeah. This is in your book too if you need to look at it, but yeah. Or you can take, hey, this one's already been uploaded. Did I open it? Is it already uploaded? Oh yeah. Hey. I just forgot. I did it last week. That was such a long time ago. All right. So if you need this PowerPoint, it's there in the Moodle. All right. Inconel. Everybody good with Inconel? Inconel. Also very much like stainless steel, good qualities, but also very corrosion resistant. Why are we using stainless steel and Inconel on exhaust systems? Strength. Any other reasons? Yes, corrosion resistant.
Inconel is porous, it's more heat resistant.
It is more heat resistant. Okay, good. And then we can mix that with some stainless steel so that we get. Trying to remember which. Sorry, off the top of my head, is Inconel more flexible than stainless steel?
It is more flexible, yes.
And that's why we're mixing it. Stainless steel gives us the better protection. Inconel gives us the flexibility as you're going down the road.
I believe also the turbines on the engines, those are also new Inconel.
Yeah, and thrust reversers. Yeah, correct. Stainless steel, Inconel, thrust reversers, because they're exposed to a wide range. Any questions before I give you a break? All right, why don't you come back at 40? 840, we'll hit non-ferrous materials.
Yeah, it's a unit. It's
All right. Oh, non-ferrous materials.
It's a unit of lift.
It's a unit. It's more than just lead.
It's like,
Aluminum, we have good malleability with it. Hey, I got things to talk about. All right, so aluminum, good malleability and ductility. It's able to be molded really well, but if you used landing gear, or aluminum on a landing gear, it would not be resilient to the abuse that it's subjected to every single day. Okay? Good corrosion resistant. When do you ever see aluminum that is absolutely just shredded apart with rust? Nothing. What happens to aluminum when it's subjected to the elements? Corrosion. What type of corrosion? Ooh, let's be specific. Okay, thank you. Corrosion is oxidation, yep. But it's surface corrosion on the outside. The cool thing about aluminum is that when it is subjected to the elements, the outside gets slightly corroded, but it creates a protective barrier for everything inside. Over time, though, the outside corrosion will begin to chip away at the external structure. Instead of rust, what happens to a vehicle when it's subjected to Michigan? Okay, thank you, friend. Frame death. Okay, great. The rust begins to penetrate all the way through very quickly versus a non-ferrous material. Okay? So, aluminum is highly corrosion resistant. High strength to weight ratio. Though it's very, very small, very, very light, it will take a lot of abuse. Not all the abuse, but a lot of the abuse. Okay? Working with aluminum, if you sit here and you bend aluminum back and forth, back and forth, back and forth, back and forth, it will get stronger right there to a certain point. And then, snaps, right? All right. Two major classes. We have casting alloy and wrought alloy. Casting is poured into a case or cast mold. For example, engines don't build real engines anymore. Most of our engines are all aluminum. Oh, okay, there's a rule. All right, never mind. Some of you engine heads, I don't call them motor heads because Tesla did that, so we'll call them engine heads. Anyway, you understand that we actually do casting. This is a sand cast, so it was a sand mold. Now they actually pour the aluminum into a certain mold. For example, like this. This is aluminum. Cast aluminum is poured into a casting. Okay, how do they pour it? Well, it's got to be hot in order to pour it. Okay, so it's melted. It's put into a pot of all mixtures of the certain material versus a wrought alloy can be used by rolling, drawing. What's the advantage of a wrought over a casting? Anybody know off the top of your head? What's an advantage, one advantage of it? There's several, but what is one?
The rod is stronger.
It is stronger because it's not necessarily taken all the way to a liquid point. Okay, so you can build a certain material up with a wrought alloy. You can build up certain layers of material. For example, on an airplane, we add copper, and then on the outside we add an aluminum coating to it to add a protective coating, and then you have a copper base middle so that it will actually bend and take the vibration of the turbulence outside the aircraft. Okay? All right. Any questions, thoughts? Yeah.
I guess I was gonna say, you could probably, you could do a lot more crazy shapes with athlete stuff on a print, right?
You can, correct. You can. But because of the breakdown all the way to a liquid, it's not very strong externally. Okay, it can, well, surface strong, I'm saying, all the way through and through is not strong.
You know, it's kind of like the process of using, but as you're working at home, does it always get harder, or is there a process that can make it actually more fun?
Yeah, you can actually make a process that makes it more and get soft. We'll look at that. Oh, sorry, I skipped two here. All right, aluminum casting alloys. As a mechanic, you will not be casting aluminum alloy parts. Just probably not going to happen. Basically, take on and take off. Sounds like automotive world, doesn't it? Oh, there you go. There's an alternator bracket off a vehicle. Okay. We don't typically recast a part. Right? We sell it to another country so they can rip us off and then sell it back to us, right? So cast aluminum has its own numbering identification system separate from the wrought aluminum system, specific shape and part. But as David had already insinuated, we can get a lot of cool shapes and sizes. We can even add cool little lines to make it look pretty, right? Okay? Yeah, they are cool. On an alternator bracket. All right, wrought aluminum. We have two classes. We have heat treatable, so it's heated to a temperature long enough. This is right in your wheelhouse right here. Heated to a temperature long enough for an alloying element to enter the solid solution, and then it's quenched, and then let to age naturally, or it could be aged in an oven or in a, what do they say? I'm trying to think of what the term they use in the book. It says in a it's like when you manipulate the oven temperature, like 3 hours at this temp, 3 hours at this temp, and then 3 hours at this temp. You step it down. Okay. Controlled. Thank you. Controlled environment. Thank you. Non-heat treatable, hardened by cold working. Additional heat treating would destroy the hardness. So we get non-heat treated, and so it says we're going to work a certain material until we get a certain strength rating. And then we don't want to go any more because additional heating would destroy the hardness. So it may be the point that you heat it to a certain temperature, and we'll get into T numbers where it's T1, T2, T3, T4, which you don't need to know right now. But once we get to that hardness, we need to get the aluminum needs to be exposed for 30 minutes. We'll put the piece of aluminum for 30 minutes at 250 degrees Fahrenheit. And then you hold it for 30 minutes, and then you back the heat away. Okay? Do not expose it again to that heat treatment, or it could break it down. Wrought alloy identification. Okay, just as we did for ferrous, now we're doing non-ferrous. They don't follow the same numbering system because we don't add carbon to aluminum. Okay, remember the last two digits there, carbon. So we have a 4-digit system with aluminum. Rest of the world may call it aluminum. So if you run into aluminum, okay. So pure aluminum group, no alloying agents, 1000 series. Example 1100 is 99% commercially pure. And then we get to 2000, 8000 group, primary alloying element identified by the first number. 2000 copper, 3000 manganese, 4000 series is silicon. 9000 series is unused. Okay? So aviation, we use 1100 series, or we use a 2000 series, 2024, 2023, 2024, 2023. Okay? Is typically what our wings are made out of. 2024. As with steel, the first digit indicates the major alloying agent. So 2000 means that copper is a primary element added to it. 5000 means that manganese is a major alloying element added to it. So you've got to know already off the top of your head, it's a ferrous material or non-ferrous material. Okay? Because there's two different tables. If you're doing ferrous, 5000 series, is 5000 series magnesium?
Yeah.
On a ferrous. And then we get over here to non-ferrous material, we get manganese at 5000. So please, you've got two different tables for ferrous versus non-ferrous material. Both are a metal, but one's corrosive, and one's non-corrosive. Or, sorry, iron-based. One's iron-based, one's iron-based. Second number indicates the number of controls the manufacturer has placed on individual impurities. So 1000 series group has 0 special control, but one would indicate one special, and then indications, alloy modification for the rest of the group. So 5083, the first modification would be 5183. So if they've done something special, the second number is an indicator of the special control. Okay. Do we know what the special control is? Nope. You could go back to the manufacturer to find out. Okay. Third and fourth numbers. In the pure aluminum group 1000, they indicate purity. So the first 99% of the aluminum is assumed. So 1030 would be 99.3% pure aluminum with no special control impurities. What's the benefit of pure aluminum? Yes, Dave. Super corrosion resistant. What's the fallacy with pure aluminum? Heat tolerance?
Really soft.
Soft. If we did pistons that were made from 1000 series aluminum, inside a cylinder and we expose it to what? Air, fuel, and spark. You would have about a 3-day life cycle of every engine. Okay? So, couldn't use pure, absolutely pure aluminum. So for the rest of these groups, third and fourth numbers are just a recipe identifier. They are just a name for specific mixture of alloys. 3,000 manganese, 3,000 or 0, no alloy modification, and then number assigned to this alloy, no other significance. Okay, so do we really know what's in it? For example, 2024. Do I really know? I know it's copper clad aluminum. That's it. Okay, and then that 2024 would be the recipe identifiers telling us how the manufacturer did it. Okay, more of a manufacturing process, which we don't manufacture aluminum ourselves. All right, so Cheddar asked this question. We have a temper or hardness. Aluminum itself is very soft. Very, very soft. So we want to make it hard. Designated by a suffix after material designation, T3. T3, various letters or numbers after the specific alloy and how they're identified. Let me get out of this real quick and see if I can open another PowerPoint. Okay, so T1 would be cooled from a high temperature forming process and naturally aged. So you take it up all the way super high, and then you're going to naturally age it, meaning it's exposed to whatever the room temperature is. And then number 2, T2, cooled from a high temperature forming process and then cold work, so then they form it, cold work it to get the certain strength, and then they're going to leave it exposed to the outside or the room temperature. T3, solution heat treated. So they'll put a certain solution. It could be a spray, could be an oil, a petroleum product. It's going to be solution treated and then cold worked and naturally aged. And then T4, be a solution treated and naturally aged. Okay. Other letters that you need to know just to be able to recognize as part of your core knowledge. You can take a picture of this slide or you can get it off Moodle, whatever. But there are letters that you need to know. Now, you need to know 2000 series and 1000 series aluminum. You just need to know it. Okay? You need to know the rest of the suffixes, no. But you need to know what a 2000 and what a 1000 series is. 1000, pure aluminum, soft. 2000 is copper-clad aluminum, typically used on wings. Boom. You got it. That's where we need to know. Baseline. That's what you need to know as part of your core knowledge. But after those numbers, you're going to have certain identifiers as an F, O, or T. Okay? F as fabricated. So boom, once I formed it, I didn't do anything else. As fabricated. O being annealed. Annealed. If you don't know what anneal is, we'll talk through it. We're going to have to talk about annealing quite a bit. So just remember O, when referenced to aluminum, is annealed. T means that it has been heat treated. And as you can tell, there's various aspects of T1, T2, T3, T4. So T just means it's been heat treated. H has to do with hardening. It's been hardened maybe on the outside. Maybe it's exposed to heat or something else. is an example, just an example of 3003 H14. The 4 designates how hard. You don't need to memorize this. All right, 2 is quarter hard, 4 is half hard, 6 is 3/4 hard, 8 is full hard, 9 is extra hard. So, in this case, the 3003 H14 is only hardened half hard. Okay? All right, alclad aluminum. Alclad aluminum. A type of aluminum sheet that is sandwiched. It's a sandwich of pure aluminum and, of pure aluminum, and then the alloy, and then pure aluminum. Yes.
You said the 2000 series was copper clad aluminum?
Oh, I'm talking about it right now. Good. I'm glad you brought that up. So alclad aluminum. So we get to 2000 series. So we get aluminum. Then we get a little copper. And then we get another aluminum. Okay? And the copper, because we don't want the copper exposed, copper's super cool, but it's super soft. So then we want the aluminum on the outside of it to be able to protect it from all the elements. Okay? So that's why you would have pure aluminum, and then the alloy, and then pure aluminum. So what happens when I decide, man, I'm going to take a torch to this stupid piece of aluminum? And you take the torch to it, and you burn it away. What have I just done? Yeah. I have burned through the pure aluminum, then through the copper, then through the pure aluminum. So now my sandwich is now what? Rotted away. Okay? I have broken down the protective coating from the copper and molded right through it. Boom! Right through it to break down the molecular structure. Not only did I do that, I also probably destroyed the heat treatment. All those little, like, H14s or whatever, okay? I've totally just destroyed the protective heat treatment for it. Yes, sir?
Just to clarify, so it's sandwiched with pure aluminum, the aluminum and copper alloy.
Alloy, yeah. Yep.
Not like.
Yep. And you're actually going to do a test on it. Super fun. Today we'll break up and do some of it. Yep.
And as far as 2024, that's the aluminum alloy in the middle, or is that talking about the whole clad?
It's just how it's clad, but copper is actually, you'll have aluminum copper together in the middle, and then a copper aluminum on the outside.
So when we say 2024, that's aluminum clad.
Yeah, it's going to be a alclad, meaning it just means it's a mixture of copper and aluminum. Yep. Oh, I already gave you the example.
Yeah.
Here, Joe, why don't you read the example for us, buddy?
Alclad 2024 E4 is a good example of a strong aluminum alloy that is protected on both sides by a thin sheet of pure aluminum.
And the baseline of that pure, inside the pure aluminum is what? Copper. Okay?
So it's not copper clad, it's aluminum over a copper aluminum.
Yes, but if you say alloy, it's a mixture of materials, and that clad, alclad, being aluminum cladded or coated, protected over it. All right, cannot be repeatedly heat treated without harmful effects. Let's ask a writer, see if he's firing on cylinders today. Why couldn't it be heat treated over and over and over again?
Well, maybe just kind of what you just said, like eventually rot away from that.
Man, he's on it today. Good. Just making sure everybody's listening. All right, good. All right, magnesium. Magnesium is the world's lightest structure metal and super fun to light on fire. 10 million pounds in a cubic mile of seawater. Okay? Also why we are creationists and not evolutionists, because if it's getting saltier and saltier, have you ever done this research?
Right.
If you have a chance to look at it. If it gets saltier and saltier, every year the world would be, the oceans would actually have been pure salt after only 25,000 years. But it's not pure salt, is it? No, it's salt water. All right. Little 10 million pounds of cubic mile of seawater, lighter than aluminum by 18%. It has the highest strength to weight ratio. As we already talked about, his little footrest, I'm going to take it from him. Okay, it's super light, super cool, but we can't build airplanes out of magnesium, as we've learned, because it becomes brittle, especially when exposed to heat. More potential fire hazard. Okay, thank you Volkswagen for demonstrating the fire hazard. How many of you have ever seen a Volkswagen on the side of the road with the owner back behind it like, oh, it's on fire, right? I used to show this picture, but it offended Dean, so I quit showing the picture of the guy with the Volkswagen in front, and he's like, ah! You know, he's in tears because his Volkswagen engine, which is air-cooled, is in the back of the car on fire. They're magnesium engines. So it was always like, you're putting air, fuel, and spark inside a magnesium. Result, if it's air-cooled, is fire. Those of you who have HVAC relatives, they pull those little pieces of magnesium out of those boilers. They're super fun to light on fire. Okay, you'll need sunglasses if you ever do that. Please don't go rip them off because I said it. You know, don't be a criminal. But if somebody does take them out and you light them in the fire, it takes about 4 or 5 minutes to get that magnesium hot enough, but then it will turn as bright. It feels like it's as bright as the sun, where you can't look at it anymore. But super amazing how hot and how bright it is. One of the products of magnesium combustion is oxygen. So when you're flying along and the big spinny thing out in front of the engine is adding oxygen to an already flammable material, Lycoming had to recall thousands upon thousands upon thousands upon thousands of engines because they put a magnesium sump on their engines. And as they were vibrating, the oil would leak, light on fire, and the pilot would get really sweaty in a hurry. Somebody had a question? Yes, Shane.
Like 10 million pounds in a cubic mile of seawater, is that the magnesium content of the water?
Correct.
There's 10 million pounds of magnesium in a cubic mile of seawater?
It's insane.
That's incredible.
Yeah, it is a renewable source because our oceans get saltier every year. And so we could use magnesium, you know, we were talking about which, by the way, is criminal. But when they're doing furnaces and boilers and stuff like that, that is actually a renewable resource that they're using within those, when they're using magnesium for those heaters. It's pretty cool. But
Oh, it's actually made out of salt in water.
yeah, and
That's really cool.
if you go back and look at how magnesium is formed, I won't show a video just because we'll get bogged down in it, and I already have 40 more slides today. So, but as I said, if you really get into the nitty gritty of this, it just reveals just how, man, there's a super amazing designer. Okay, titanium, approximately 60% heavier than aluminum and 50% lighter than steel. I love titanium. Titanium is so cool, isn't it? So stinking expensive, but so cool. Okay. I remember one of my coworkers wanted us to take a titanium sprocket and cut it out for his wedding ring. And I still remember grinding on that silly sprocket, trying to make a wedding ring out of it forever and ever because titanium is so hard. Okay. It has a high melting point, makes it good for firewalls, but it's not strong enough if it's exposed to 1,000 degrees. Anybody know what an EGT runs on our aircraft? What is EGT redline? Any guesses? Okay, good. 1600 or so. Somewhere 16 to 1650 is redline on your exhaust gas temperature. So, if we use that on our firewall, anybody see a problem? Oh no, There was an exhaust leak and now the firewall is liquid. Okay? It's not a real good scenario. Okay? Okay? So only non-ferrous that can be case hardened. Okay? You're asking what's case hardened? It's a great question. You'll have the opportunity to look up that definition for your lab today. Okay? Copper. It's a great conductor. Fantastic conductor. Way overpriced in America, but it's a great conductor, but very, very heavy. Okay? If you take the same electrical cable, same size electrical cable, copper, and you use the same one that's aluminum, aluminum is going to be about half the weight of that copper, but it won't carry the amps that the copper would carry. Okay? Strength ranges from 25,000 psi to 200,000 for beryllium copper. Good for small parts that need to be wear and fatigue resistant, bushings or bearings. Okay. We don't really use copper a lot anymore. We mostly use bronze bushings. But they did use copper bushings at times. All right, I'm going to stop. Should I stop? Should I? No. Let me hit one more slide. Yay. Yay. Okay. Malleability. Ability to be shaped without cracking or breaking. I already talked about this, didn't I? Why did I skip that? Did I do brittleness already? Oh, wait. Why did it skip down? Oh, there we go. Okay. Metal working process. So 3 methods. We have hot working, we have cold working, and we have extruding. Hot working, cold working, and extruding. Okay, Caleb Rose, what is hot working? Good. All right. To form it into a certain way that we want it. Cold working, what's cold working? Rolling, bending on it while it's at below its critical temperature. What is extruding, and what is the benefit of extruding? Shane. Good. All right. So, for example, let me see if I have a picture of this. Oh, I do have a picture. So, we get a material with extruding, and we have not reached its critical temperature. Okay? Let's use steel, for example. Anybody remember what roughly the critical temperature for steel is? 2600. Okay? So say we raise it to 2400. What's the benefit of extruding is that we haven't meshed all those materials all in as a liquid together. Okay? So we're still keeping maybe we would say, layers of material separated. But we're taking the temperature way up. We've not quite deformed or made the materials mesh together. Then we take a ramrod and we ram it through a die. And out comes a product that has been extruded, but is still maintaining molecular division or molecular structure without liquefying it, right? All right? That's about as simple as I know how to describe it. Here's a cute picture of cold working. That's a honking piece of metal. All right, so they're going to roll it, shape it, while it's still fairly cool.
What is fairly cool?
Just based on what material they're actually using. You know, if it was titanium, it would be a lot lower. If it's steel, it could be between 15 and 2,000 degrees. If they're able to actually get it formed, yeah. Still staying away from that critical temp. Somewhere. It's just based on what material they're using. I mean, stainless steel could be higher. Yeah. Hot working. Hot working, almost all steel is hot worked into a form, often harder or too brittle after hot work. To temper it relieves the strain and reduces brittleness. It always, 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 always follows hardening. Okay? And then they have the option to anneal it, which will relieve some of the strain and soften it. Okay? And then normalizing is only iron-based metals only. That is actually a written question. Is normalized, or how does the written question go? What is the only, something about what is the only process used in ferrous materials, and it will be normalizing. Okay, I have a video for carburizing, and then I'll give you, we'll break you up into groups. Oh, I have a definition. Let's do normalizing first. Normalizing removes internal stresses derived from heat treating, welding, casting, forming, or machining. By the way, it's only used for iron-based or ferrous materials. All right, carburizing. Let's do this video if I can.
Hello everybody. For those who've watched my videos before, you would know that I like to build things like bots, robots, AI, and other tech stuff. However, what you might not know is that I like to build pretty much anything. I've built boats, furniture, I do lots of landscaping, fixing up the house, and recently, while looking for further projects to keep me busy during lockdown, I thought I would try something new, making knives. In fact, this is one example that my son and I put together, our first try. It's a Viking style sea-axe or sax. Don't worry, it's not actually sharp, but it is rather pointy. The problem is, you need high carbon steel for making decent knives, at least those that hold an edge. And that is hard to find and very expensive. However, due to the YouTube algorithm feeding me with videos on my latest interest, I discovered it's possible to carbonize low quality steel. Even more interestingly, this carbonizes from the outside in, leaving a flexible, low-carbon steel core surrounded by hardened, high-carbon steel. The result should be a blade somewhat like a differentially hardened katana blade, flexible, yet with a durable edge. Sounds promising. So, as another interesting lockdown project, I thought I would test this theory. I'll put a link in the comments to the video that gave me the idea so you can learn from that video as well as the process I go through here. But let's talk about the plan. I figure if I make two small lengths of katana-sized blades, carburize one of them, then we'll have a simulated sword fight between the two and we'll see how each of the edges holds up. I'm making this video progressively as I work, so at this stage, even I don't know how this is going to work out. So let's take a look at how things go. I started with a cheap $20-odd 7mm thick steel lintel from my local hardware. These are galvanized, so firstly I had to ground off the zinc coating to expose the steel underneath. Then I ground an edge onto one side and cut out two short lengths that I could use for the testing. One will be carburized as part of the heat treating and then quenched in oil. The other will simply be heat treated and quenched in oil, which is the standard approach to harden high carbon steel. Now the video that I watched called for a mixture of salt, flour and some form of carbon. I'm not quite sure the role of the salt, but I'm assuming the flour is there to sort of bind it all together into a kind of dough you can wrap around your steel samples. For the carbon, what I did was smash up some charcoal that I'd purchased from the local hardware shop also into a very fine powder, and then I mixed these together in the suggested ratio of 6 parts of carbon with 4 parts of salt and 3 parts of flour. Then, after mixing these thoroughly, I added in a little bit of water to make a thick paste, and what you then do is take this and you wrap it around the steel samples, as you can see in the video here. You want to ensure that you coat well the edge where you want the carbon to be absorbed to harden the steel. And while I covered the whole thing, I'm not sure that's so important unless you need the entire piece of steel to be hardened. The carbon wrapped sample was then left to dry along with the uncarbon wrapped sample and a knife blank that I'd also created and wanted to carbonize. Now I want these to dry out pretty well because the process of carbonizing should be done without oxygen. So you wrap the carbon wrapped sample in clay. That prevents any air getting inside, so as long as there's no moisture being given off, I'm not going to potentially create steam and break the clay wrapper around the sample as we're carburizing it in the forge. And as you can see, there's a small cut in one of the samples which will allow us to differentiate them later on when we're doing our testing. The clay was fast drying, so it just needed a few days to dry, and then I put it into my simple backyard forge, surrounded by some charcoal barbecue bricks. Then, with the addition of some forced air, I left it to cook at high heat for around 2 hours to hopefully absorb those carbon atoms. Before quenching, I warmed up the oil a little, using a hot piece of steel to ensure it was viscous enough to cool our samples properly, which is something else I learned from YouTube. While my carbon wrapped sample was cooking, I heated up my control piece in the forge and then quenched it in the oil, much like you would heat treat high carbon steel. This was to ensure that the only difference between the two was the carbon treatment process. After around 2 hours, I took out the clay and carbon wrapped sample. On a heat-proof surface, I carefully broke it open. The steel inside looked like it had been heating up very well, and hopefully therefore had been absorbing carbon from the charcoal, salt and flour mixture wrapped around it. Then I quenched it in oil, just like with the non-carbon wrapped sample. After they had cooled down, I tempered them in the oven on an old pizza tray for an hour at 200 degrees. Now that we have our two samples, the first test is to run a file across each sample and see how well the file can penetrate the steel. First, I tested our control sample. Then I ran the file across the carburized sample. I tried to use the same pressure and length of the strokes as I did with the first sample. Finally, I compared the file marks. You can see that the file does seem to have penetrated deeper on the non-carburized sample. So, after our first test, it does seem we've improved the steel. But the real test is, whose sword will win in battle? Because nobody's going to bring a file to a sword fight. So, to test this, I needed a way to bring one blade down hard against the other in a controlled fashion. As you can see here, I did that by putting one piece in my trusty vise, holding the other with vise grips, and then using a rubber mallet to cause a collision. And just in case it somehow mattered which one was in the vise, I made sure I swapped around the samples so that I was approaching this whole test in a scientific manner. And frankly, I was shocked by the result, in a good way. The control sample has deep gouges where the two edges collided, while the carburized edge is barely scratched. In fact, I can drag my fingernail along it and there's no dent in the edge at all. But would our carburized sword have snapped in the midst of battle? Well, let's try the whack it with a hammer test. It seems that because the core of the blade is still flexible steel, that it resists a strong blow with the hammer. So, I guess I've proven that you don't need special steel to make a strong blade. Fun historical fact, this is part of the process that was used to produce Damascus steel, which was renowned for its strength and hardness. So, when COVID morphs into a zombifying virus, get yourself a grinder, a bag of charcoal, some clay, and a cheap steel lintel from your local hardware, and you'll be set, because there's only two ways to kill a zombie: fire and taking their heads off. So, thank you for watching this video. That's the end. As I mentioned, it's a little bit more hands-on than my normal technology videos. I'm off to prepare for the forthcoming
Sorry for the violence. I do not condone violence. terminologies are listed in section 4 of AC 4313. For example, if you need to know metallic versus non-metallic, I'm looking for a specific. So there's various methods to be able to test the hardness of material. To be able to test hardness of material, sometimes we'll use something called a Brenner tester. There's a Rockwell tester, hardness testing, figuring out how hard something is. For example, who has the digital version? The digital version of AC 4313 open right now. Can you look up sodium hydroxide for me?
I don't.
Oh, may I have the search function on tell me what paragraph is it in the new one? Mine's different from yours, that's what I was trying to figure out.
Paragraph B of 423.
423. Okay, I don't have it there. That's interesting. All right, I'll have you read it when we get there, okay? So, this is important because, for example, brakes. Brake pads. You ever thought about how brake pads are made? Brake pads. What is supposed to wear first when you push on your car brakes? The actual pads are what we call in aviation linings. You don't want the disc or the rotors to wear. Okay, we call them disc. Car calls them rotors. You don't want those to wear. You want the linings to wear. But how much? How little? Well, that's where we come into a Brenner tester. You have a Brenner tester or a Rockwell tester. So my friends at Rapco sent us a video. I'll show you how they test brake linings. A friend of mine was working there, and so they sent us a video. His name was Elliot, and so he told his boss, hey, can you help us out and show us how you test brake linings for Learjet? He said, I'll be happy to. So I'll show you how the Rockwell tester does that, okay? So here's a Rockwell tester. They'll put a test piece in there, and it has to hold a certain load. Anyone ever used a Rockwell tester? Okay, you have. Pretty cool how they will test to make sure it holds a certain load, okay? All right, so here's Kim. It will change directions. Just give me a second.
All right, everybody, this is Kim. Say hi, Kim. And this is our mid-tutorial Rockwell hardness tester in the HRC scale. As you'll notice, there are two needles. We have a curved needle and a straight needle. At the very bottom, you'll see a red line by the 50, and it says set. Here's our punch, needle tip. This is a wheel that adjusts this whole thing up and down. On this side, you'll see an arm. This arm is connected to free weights. So the way that you use this is you throw your part. In this case, we have a wear pad in. You throw your part in. We're going to adjust the wheel until the curved needle sits in that red. There we go. We'll put it as center as we can in the red line. We're going to lift this gently, let the free weights drop to do their thing, in which case they are going to press this punch down. And it's going to keep pressing it or pressing on it until it stops, and then that's how it tests the hardness. Then we're going to drop this bar down to drop the free weights, and it'll tell us our hardness.
And it's wrong.
It's wrong because she measured in the same exact spot as the last time that she measured. So, if you'll look at the part now, hand me the part. You'll see these little divots. See those little punches? You see three little holes? If you measure in the same one, you're going to get a different reading. So, we're going to do this one more time. We do our parts, or at least these parts, to 32 to 38 Rockwell. So now we're going to do this again. Lift up gently, let the free weights do their thing to put pressure on that tip. Once it comes down, once this stops moving completely, you can drop it down, and you'll see your reading. Right now, that's 35, HRC. Thank you so much. Elliot, hope that helps. Love you, brother. All right.
Sorry, I know it's a little bit to the side. So what they do is they'll do a certain, as they're producing these brake linings, they will test the whole batch that comes through. They will test them. They'll grab a few of them off the assembly line and they'll take them in and they'll test them to say, hey, they hold up to this rating, okay? And so they're putting that in there just to verify that across the board, these brake linings are holding up to the same standard, okay? And you appreciate that because when you push your brakes, they don't all of a sudden have to get changed once a month, right? And so that's what they're holding up to, in this case, a 35, even though she did it wrong again. Yes?
So that number, the higher it is, the harder, or the lower it is, the harder?
Well, it's based on a certain weight, so, let's see, it would be the outside, so, yeah, in this case, the lower that hardness number was indicating was like a, I guess you would have a higher rating, it's withstanding more weight. Yeah. So he does it. They do this all day long. They get a batch through. Hey, we got 30,000 brake linings. They'll grab. Could be 10 out of a batch of 30,000. That way, if they're coming back too weak, they can stop the batch and say, hey, it's too weak. Let's get another one. Make sense? That's what I got for today. Sodium hydroxide. Let's talk about testing aluminum. How do you know when you grab a piece of aluminum that it is either 11,000 series or 2,000 series? How would you know? I mean 1100 series or 2,000 series? How would you know? So AC 4313 gives us an approved method for testing. Give me the page number in your book. 411. 411.
I have 410 in the paper.
Whoa.
And a lot of them testing.
Totally different. Totally different. All right, you want to read it for us, or do you? Here, no. Let's let Grant read it for us. How about Grant read it for us? Go ahead.
Test for distinguishing heat treatable and non-heat treatable aluminum alloys. If for any reason the identification mark of the alloy is not on the material, it is possible to distinguish between some heat treatable alloys and some non-heat treatable alloys by immersing a sample of the material in a 10% solution of caustic soda, sodium hydroxide.
Okay, stop right there. So if you go and you grab aluminum, it's been in the shop for some time, those little printed numbers go away. Or if you're doing a panel repair, oh no, Ryan did not tighten the panel down all the way and it came off and now it's bent. So then I need to make a new panel. Can I do that? Absolutely. So I go over to the scrap aluminum because I'm not going to get a brand new sheet. How do I know that it's 2024 and not 1100 series? Well, in this case, you'll take a sample. You do not use the same piece of aluminum that you're going to put on the aircraft. You use a scrap piece of aluminum. Okay? So if I have a sheet this big and I only need a panel like that, you take a portion over here. You take it with pliers and you shove it in a sodium hydroxide solution. What's another name for sodium hydroxide? Drano. As you know, Menard sells it. You go in, fourth row on the left, bottom shelf, right there in Columbus. There it is. Okay? You can go in there and you can get Drano, sodium hydroxide. Pure sodium hydroxide gets very, very hot, and when it comes in contact with water and copper, it lets off a horrific smell. But what's super cool is the copper will turn black. And because you've cut the sheet, you've exposed the side of it. And it will show you, this is copper, 2024. All those numbers that we just went over, they matter. If it's beautiful silver, then guess what? What type of aluminum is it? 1100 series and cannot be used for a panel. Okay? How would I know what material to use on the aircraft? How do I know if it's 2021 or 2024? Any guesses? Bueller? Any guesses?
What the manufacturer says.
And that service manual will tell you, hey, this aircraft was constructed for 2024. If you go to structural repair section, typically towards the back of Cessna manuals, it will say, for these repairs on the wings, please consider using 2024 for all the following repairs. Those little paragraphs, they matter. And with the invention of Control F, you can find it right now, okay? So what we're gonna do is, I'm gonna open the lab for today. You got about an hour and 15 minutes. We're gonna do groups of 6. I'm gonna do it simple for my small brain. I'm gonna do it this way. So 1 group, 2 groups, 3 groups, 4 groups plus you 2, and then you'll be the last group, but not the least. Okay, all right. So you guys will go first, and what you're gonna do is you're gonna meet Miss Anna in, wait, the first thing you're gonna do is read the lab. And it's the last question of the lab. The rest of you guys are going to work on the other labs and the new lab that I'm opening for your enjoyment, minus the last question. So this group, but not the least group here, should have the lab fully done by the time you get in there, probably tomorrow. You got me? All right, and so then you're all going to test sodium hydroxide. Those of you who are doing the sodium hydroxide, if you're going to be the one testing it or standing over it, I would suggest you to have a mask on, and you'll definitely need gloves. You do not want it to come in contact with you. Sodium hydroxide, just heads up, does eat through hair. That's why it works as Drano really well. So we're only using a 10% solution, so it shouldn't be that dangerous. But just for safety measures, do not ingest it, do not touch your mouth after handling it, all those other safety protocols, okay? If you're not sure how to handle it, don't touch it, okay? All right, I'm opening up lab 5, number 2, or lab, those of you who did not hear me this morning early on, we do have a quiz tomorrow morning. Aircraft materials number 2 is open, and I believe there's 17 sweet questions there, with the last one being 2 samples of aluminum. Briefly read that and take off this group right here. As soon as they're done, group number 2 here, I want you ready to go. All right, so 1, 2, 3, 4, and 5. Everybody good there? Group of 6. So David and James, you're with the back row. Cheddar is waiting in the front row here. All right. You'll have to use your book and potentially AC 4313 to answer these questions on aircraft, metals, and materials. All right. You'll need safety glasses. If you don't have any, borrow some. Do not go in NDT shop without them. All right. Yes, you may work on other labs if need be.
Including the prop torquing lab?
Yep, correct. Yep. And when you've torqued it, please make sure you get a sign off and show the reference. All torquing will be done in accordance with the PA 28140, even if it's on a mock-up, because you don't want to go outside. Totally fine. You've got to show me the reference that you used for torquing that prop. and it's going to be in the PA 28-140 manual. And yes, I do know the page number. So,
Where is it signed off, though? I didn't see a spot for it to be signed off.
yeah, so I have a checklist that I sign it off when I come in. Oh, one of the other instructors.
Well, Anna said she had looked at it.
Great.
She did.